Hey there, friends. It's Miss Adams from Flamingo Math. We have a one-day lesson in section 4.9 all about vector valued functions. This is a good topic if you're planning on going into a BC calculus or calculus 2 in a university. We're going to explore vector form of parametric equations where x is f of t and y is g of t, and f and g are going to be continuous functions of t on some interval I. We've only considered functions where the domain and the range are sets of real numbers or real valued functions. A vector valued function receives a scalar as an input and returns a vector as an output. We're going to work with vector valued functions on a two-dimensional plane, but they are also valuable tools in three-dimensional space, which would be in a college or university course. Now we want to represent motion along a curve by giving a definition to a vector valued function where the domain consists of real numbers and maps the range to a set of vectors. So in two dimensions, the position of a particle moving in a plane that's given by parametric function f of t can be represented as a vector valued function in the form of x of t, y of t, this is component form, or in linear combination form, xt of I plus yt of j. The magnitude of the position vector at time t gives us the distance of the particle from the origin. So this is all new information to us. Let's consider a vector valued function describes all the vectors that begin at the origin and have an endpoint at some x of t, y of t for every real number t. So consider the vector valued function f of t is t plus 3, comma, t squared. We can complete the table here with that information. T plus 3 gives us 0 for x, 9 for y, so we have the ordered pair 0, 9. If you continue down the table, we can complete the table to give us a foundation for where we can graph. So we'll just finish this up real quick. And then we're going to go over to our graph and graph those ordered pairs onto the grid. So 0, 9, 1, 4, 2, 1, 3, 0, 4, 1, 5, 4, and 6, 9. You see what happens here? We formed a parabola represented by the vector valued function. And by our definition, it describes all the vectors that begin at the origin. So we can also say we begin at the origin and we go over here to this ordered pair at 5, 4, and from the origin, the distance up to our final point at 6, 9. So f of x on part D, f of x, can you write a function rule for the shape that's traced out by the vector endpoints? Well, sure, that's easy. We can say that f of x is the quantity x minus 3 squared, because we know about transformations of polynomials. This is a parabola that shifted 3 units to the right. So in our first example, we saw that the function traced out the shape of a parabola. With the function rule that we wrote down x minus 3 quantity squared, each point along the curve simply represents a point in space. But in the vector valued function where we have t plus 3 comma t squared, each point represents a vector. So we can use the information on the graph to find magnitudes and angles of direction, or we can perform operations on those vectors. For example 2, we want to express the parametric equations x equals 5 cosine t, y equals 3 sine t is a vector valued function, and then sketch the curve. You can check it with your calculator. Following the rules that were given to us, the vector valued function, if I call it f of t, vector valued, it's going to be 5 cosine t in the I direction and 3 sine t in the j direction. You can also write that in component form. F of t is 5 cosine t, comma 3 sine t. Now what does that tell us? It tells us we have an ellipse whose center is at the origin. In the x direction, we're going out 5. In the y direction, we're going out 3. And tracing that smooth curve, the shape is going to be an ellipse. And each point along that curve, like it's set up here, each point represents a vector. So there's an infinite number of vectors from the origin out to any point on our curve that represents the distance from the origin to the curve. Let's find the domain of vector valued functions in the next example. The domain of a vector function is the intersection of the domains of the component of functions f and g. To find the domain for a vector valued function in component form, we must find the values of t where f is continuous at both the f value and the g value. So if we're given the vector function here, t squared plus 1 in the x direction and natural log of t minus 2 in the y direction, we want to find the x of f of t. So the x of t is going to be the t squared plus 1 component, and the y of t is going to be the natural log of 2 minus t, that quantity. Finding the domain of f, we know that natural log 2 minus t has to be greater than 0, so t is going to be less than 2. But the domain of t squared plus 1 is going to have a domain of all reals, so there's no restriction on the x of t component. What would be the intersection of the components is what we would call the domain of the vector valued function. So the intersection of our components are going to be, when I'm going to write this, the domain of f is going to be from negative infinity up to 2, not including 2. We can also use vector valued functions to express the velocity of a particle in a plane at different times t. At time t, the sign of x of t indicates if the particle is moving right or left, and the sign of y of t indicates if the particle is moving up or down. The magnitude of the velocity vector at time t gives us the speed of the particle. The magnitude of the velocity. Let's check that out with this example 4. The velocity of a particle moving along a path can be modeled by the vector valued function v of t. Find the v of 1. Well, the v of 1 is found by substituting 1 in place of t, so that would be 2, 4. What does that tell us? It tells us the particle moves to the right because the x of 1 is greater than 0, it's positive, and we also know since the particle moves up because the y of 1 is also greater than 0. They were both positive values. Find the speed of the particle at this time. The magnitude of vector v is 2 squared plus 4 squared. So that's 16 plus 4, that's 20. The magnitude of vector v is 2 square roots of 5, or the square root of 20, units divided by time. In example 5, we want to find the magnitude and the angle for g of t at t equals 4. Well, first we need the g of 4. The g of 4 is 4 plus 1, that's 5i, and 4 squared, that's 16j. And then we want the magnitude of the g of 4. So that would be the square root of 25 plus 16 squared. That's square root of 281, I believe. So this is our magnitude. And we want the angle. The angle would be where theta is tan inverse of 16 divided by 5, and I need my calculator to do that. So tan inverse is 1.268 radians, the angle. Now let's talk about displacement. If we let f be a vector valued function and the first time sub 0 is less than time sub 1 be values in the domain, the displacement of f from t sub 0 to t sub 1 is f of t sub 1 minus f of t sub 0. Oh boy, that looks like we're going to see rates of change here in a minute. The displacement vector is drawn with the initial point at f of t sub 0 and its terminal point at f of t sub 1. So if an object moves along the path that's given by f of t, this looks like a circle to me, we want to sketch the curve on the grid provided that time goes from 0 to pi. So we're only going to draw half of that circle. So from 0 to pi, it'd be up 3 and left and right 3. And we want to very carefully, that's hard for me to draw this semicircle there. And we know that the motion along that curve is going in a counterclockwise direction. Find the displacement from 0 to pi. So the displacement by the definition above is -3, 0 minus 3, 0. The displacement is -6, 0. You see what that told us? This is the displacement. We traveled that distance. Sketch the displacement vector. So really and truly, I just want no arrow on that end. The displacement vector starts here and ends over here, 6 units to the left. Explain the meaning in relation to the object. The object ended up at a distance 6 units from its initial location. Let's write that in a complete sentence. And we knew that because the object started at the point 3, 0 and terminated at the point -3, 0 when our angle was pi. Then in our last example, I knew average rate was coming. If we know the distance from a starting point, it allows us to compute the average rate of change, where f of t is a vector valued function and each of its component functions is continuous on its domain, where we're letting t sub 0 be less than t sub 1. The average rate of change of that vector valued function on the interval from t sub 0 to t sub 1 is the change in the y divided by the time. So we can look and practice on this last example for number 7. If we have an object that moves along the elliptical pathway modeled by f of t is 4 cosine t, 5 sine t on 0 to 2 pi, let's calculate the average rate of change from 1 to 2. So we're calculating the f of 2 minus the f of 1 divided by 2 minus 1. So these are vectors. You need your calculator to verify that I haven't made any mistakes. So the f of 2, 1.665, 4.546 minus 2.161, 4.207, and 2 minus 1. So our average rate of change is negative 3.826, 0.339. This is a vector. Explain the meaning in relation to the object. What is the motion of the object during this interval of time? So think about the graph with me for just a minute. We've got this elliptical shape here, and we're starting at t is 1, and we're stopping at t is 2. So we've got this kind of a shape. We're going left and up, but at a slight incline. So on average, what we know is that the particle moved left because the x component was negative, moved to the left, and it also moved up on the interval from t equals 1 to 2 inclusively, and it moved in that direction in an elliptical pathway because they gave us that at the beginning. You could graph this equation, this vector valued function, on your calculator and verify that. And for our last little exercise here, we want to find the distance of the object from the origin at t equals 2. Well, we know the value at t equals 2 from up above. So t equals 2. The f of 2 was the vector negative 1.665, 4.546. And the magnitude at 2 would be the square of negative 1.665 plus the square of 4.546 summed together, taking the square root, which is 4.841. And if you looked carefully on your calculator at that elliptical pathway, if this is 4 and this is 4, I didn't do such a hot job drawing up here. We know that from the origin out to that point, negative 1.665, 4.546, this is the magnitude, which is the vector going there. I hope that makes sense to you, and we have lesson 10 coming up tomorrow. See you then.